And all of this can run boom, at once and update your weights. And that's part of the power of the transformer architecture. And this idea, this happens during training. All right? Parallel processing. Now, what happens during inference? When you're seeking to, when you've already trained your network and you're seeking to simply translate the sentence. Let's say, same sentence, what is your name? Now we know what the answer, now we know what the translation is. Let's see what would happen given this autoregressive context. And autoregressive, this is where we would really see what autoregressive means in the context of inference, and there's a difference in the behavior. This stepwise staggered form, right, which looks like a lower triangular matrix, is the so-called causal masking that you'll see described in the Vaswani et al. Paper, all right, which is the 2017 Google paper. All right, so let's see what happens, assuming instead, say we trained this neural network on, hopefully not this exact sentence, but some other series of sentences, and now our neural network now understands Yoruba, and we now seek to translate this sentence. Let's see what happens and how it works. So one difference, clearly, is that since we're not training, we're not having to do cross-entropy. So remember here, this was not our final step, but this step during training led to one more step. I'm just going to erase this, even though it's what we're discussing. It led to a final step, which was to generate our loss function minus sum over j of t sub j log p sub j, right? And this gave us our score function, our loss, which we then did backprop on and went over and over and over during training. During inference, this is our final step. This is our final step, and whatever peaks, wherever this peak occurs, our argmax, which is a word, this is of length 45,000, I'm assuming there's 45,000 active Yoruba words in usage. This one is, in this instance, would be the word that we would utilize for our translation in the transformer. So, what happens at inference time? We've seen what happens in training time. We're very clear on that now, right? What happens during inference? During inference, we pass in the full sentence that we seek to translate, right? We pass it in with the pre-processing steps of tokenization, encoding, positional encoding, as well as word embedding, and then positional encoding, and then it goes in. It goes in, and it goes in as we've described, all the steps that would occur, we've talked about. And there's a final output layer that emerges, and then this cross-attention happens, all right? So I'm talking about that here just for space, all right? Then what? What do we do first? So what we do first is, as you guessed, the SOS token, which is the start of sentence, and we pass it in. It's the subject, meaning it's the one that generates the query. We do a self-attention. It has only itself to attend to. So self-attention happens with itself. You generate this context vector with which cross-attention then happens with everything else that's coming in, right? And what does cross-attention mean? Again, it simply means that this is the query and those are the keys. And then another context vector emerges from there, and that repeats, say call that C0 to the 2 for the second layer. And then finally, that goes into our linear layer. This is a feed-forward neural network of one layer that spans and outputs a vector of length 45,000 because I'm assuming here there are 45,000 active words in Yoruba language usage. Okay? And so we get that. And then we pass that into a softmax, and we know what a softmax is by now. We've talked about it over and over. And what it generates for us is a probability distribution. Then we simply pick the maximum, the word that has the maximum peak in there. And if our network is well trained, this word should be what? Key. And when we get that word here, key means what in Yoruba? We simply pass that word in and we auto-regress it. That's what that means, auto-regress. We pass that word all the way down here, and we put it in. All right? And then we simply move our cursor. The start token has done its work as the active subject. It's still in the game, but now it is simply a member of the self-attention process. But the cursor moves, the spotlight, so to speak. And that term spotlights of attention was coined by Jürgen Schmiederer in 1991 with the fast-wave programmers. The spotlight moves to the word key. All right? And when self-attention is happening, now there are two things over which it's happening. So a key vector is generated for the SOS token and for the key token, and a query vector is generated only for the key token in this step. And then similarity is done, dot product, right? And then attention matrix is generated, and then that is used as coefficients for the value vectors. Value vectors are generated, all right? And then we get our output, which on this round, it's going to be C1, right? We call that one C0 in the first one. Let's call this one C1, context. It goes into cross-attention layer, and it cross-attends with the whole set of output from the English. What is your name? All 5 of them. Cross-attention occurs, and then let's erase this C0, and instead it's a C1. Okay? And that spans into that C1, enters the feed-forward layer, and outputs a vector of length what? You got it, 45,000. All right? That goes into a softmax and generates for us the respective probability distribution, which is going to be different from the previous one. Okay? So we're doing a real-life simulation here of our example. And there will be a different probability distribution that might look something like that, perhaps. All right? And if our model is well trained, the top word should be what? Ki, ni, should be that one. Ni is. What is your name? And then that would auto-regress and be fed in to here. All right? And what happens next? You guessed it. Our cursor moves to this word. And the process continues, ... until we finally output, at the end of all of this, until we finally output what? An EOS token for end of sentence. When we do that, we're done. That's our signal to say you have done your job, EOS, and you can stop now. Why is that important? It's important because the length, depending on the language you're translating, what is your name? What is your name? How many words? What is your name? What about Yoruba? How many words? 1, 2, 3, 4. We got lucky, okay? But the point I was trying to make is that the length of the sentence can be very different in different languages, and so you have no hard coding for how long this can be or how short it can be. And so whenever your well-trained neural network is done, it would let you know, it needs to let you know that it's done by outputting for you an end of sentence token. Great. So now we've seen the transformer, we've seen how it works in its full form. Very important is for large language models, we need to understand that you can simply disconnect this, right? Clearly, if you do, there would not be a cross-attention layer if there's no encoder layer. And that's often the case for instance, in the GPT a family of models like ChatGPT, for instance. Those are decoder-only models. BERT, on the other hand, is an encoder-only model. And there's just a difference in the way that they're trained. In the case of encoder-only models, you would typically have input values that have some masking in them, right? You might put a mask here and do sort of a fill-in-the-blank type of task, feed in that encoder, and when you feed it in, you would force it to learn what this word is, because your final layer will now have an output that does a softmax, generates a probability, and next has a final layer of a cross entropy loss where you know the answer. So you force the network to learn the answer, right? And it's amazing that's how these almost probably precursors of some form of, a lot of people believe, of semblance of intelligence. Keyword is semblance. That's the operative term. Seems like. Comes from just really forcing things to learn, fill in the blanks, and there's a staggering amount of context that a model has to learn so as to be able to fill in the next word. And if you were training a decoder-only model, the task would be, what's the next word in this sentence? That's your training data, like we had here. So you have this, and then you would have a cross entropy loss on top of that, where you know the answer, what the next word should be. So this would be predict the next word type sentence. And then you can also have additional tasks that are higher level tasks, like sentence summarization, like question answer, and so on, where you're feeding in something and you know the answer. That's it. That's all you have to have. All you have to have. This is all supervised learning, end-to-end training of neural networks. That's what this is. Okay. So you could have a paragraph from the New York Times, or you could have a page from the New York Times as training data, and the label for that data is a 2-sentence summary. And so you can design all sorts of experiments around this. And so there's the idea of fine-tuning of large language models, which requires sometimes a significant amount of resources, in that there's human input that has to sort of be involved, and you have very highly curated data sets. So the general trend now is that these models are trained on massive amounts of data. The general base models of these neural networks can be trained on, like, English Wikipedia, the Toronto Book Corpus. We're talking about lots and lots of 1 trillion words, for instance. And then after that's done, there's a layer of fine-tuning as well as reinforcement learning with humans in the loop that can refine and teach, these models towards very specific domains. And that brings us, into the era of large language models, which have massive, massive applications, transformative potential across industries. And this really is the basis. The transformer architecture, in particular, the attention mechanism, are the basis of that.